All right, everyone, we're going to wrap up Module 6 by talking about limiting reagents and also percent yield. So this is the last lecture for Module 6. And let's get started. So I'm going to go ahead and share my screen and get rid of me. All right. So let's go back to our pizza recipe. Remember, our recipe had the ratio, 1 crust for every 5 ounces of tomato sauce to every 2 cups of cheese, and then my product was 1 pizza. So these were the ratios, 1 to 5 ounce to 2 to 1. Now, how many pizzas can I make if I have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce? Let's calculate the amount of pizzas, the number of pizzas that I can make from each one of these ingredients individually. If I have 4 crusts, I'm going to use the ratio for every 1 crust, I have 1 pizza. That means I can make 4 pizzas if I have 4 crusts. 10 cups of cheese. The ratio, 1 pizza takes 2 cups of cheese. I can make 5 pizzas if I have 10 cups of cheese. 15 ounces of tomato sauce. My ratio is 1 pizza for every 5 ounces. This means I can make 3 pizzas. So even though I have enough ingredients, I have enough crust to make 4 pizzas, and I have enough cheese to make 5 pizzas, I can't actually make more than 3 pizzas, because once my 15 ounces of tomato sauce runs out, I've made 3 pizza and I have no more tomato sauce. So I have excess crust and I have excess cheese, but I only have enough sauce to make 3 pizzas. That means the sauce limits the amounts of pizzas that we can make. It's called the limiting reactant or the limiting reagent. This is excess. This is excess. Well, once I run out of the tomato sauce, that 15 ounces, I have 3 pizzas. I have an extra crust and I have extra cheese. So I have enough crust for 4 pizzas, enough cheese for 5 pizzas, but I only have enough tomato sauce for only 3 pizzas. Therefore, I can only make 3. This is the yield of the pizzas. The tomato sauce actually limits how many pizzas we can make because it runs out first. So, talking in chemistry terms, the tomato sauce is the limiting reactant. And that reactant is the reactant that makes the least amount of product. You might also hear the term limiting reagent. The maximum number of pizzas I can make depends on that limiting reactant. This would be called the theoretical yield. The theoretical yield is the amount of product that can be made based on the amount of the limiting reactant. So the ingredient that makes the least amount of pizza determines how many pizzas I can make. The same exact principle applies in chemical reactions. The limiting reactant or the limiting reagent is the reactant that is present in limiting amount. It limits the amount of product that can be formed because once it runs out, there's no more of that chemical. There's no more molecules to react. So the limiting reagent determines the extent to which a chemical reaction can occur. Excess reactants are any of the reactants that I have left over after all of the limiting reactant has reacted. This theoretical yield is the amount predicted by calculations, and this is always based on the limiting reactant. I have excess reagent, I can calculate yields for those too, but I can't make that much because I have to base what I actually can make on the amount of reagent that limits the amount of product, the amount of reagent that runs out first. So if I have reactions with multiple reactants, it is very likely that one of those reactants will be completely used up before the others. When that reactant is used up, the reaction is going to stop. No more product will be made. The reactant that limits the amount of the product is called the limiting reagent. It could also be called the limiting reactant. It gets completely consumed. So at the end of the reaction, I have zero left of that limiting reactant. Reactants that are not completely consumed are called excess reactants or excess reagents. I can calculate the amount of product that can be made from the amount of limiting reagent I have, and this is always called the theoretical yield. Theoretically, that's the amount of product I can make. I calculate that based on the amount of product that runs out first. So here's an example. One way I can tell that I'm encountering a limiting reagent problem is that I have two amounts of reactants. So here's my reaction. Two magnesiums react with one O2 to form two magnesium oxides. The question is, what is the limiting reactant and how much of the product can I actually make from that amount of limiting reagent? Well, I'm going to use regular stoichiometry. I'm going to take my 42.5 grams of magnesium. I'm going to convert that to moles using the molar mass of magnesium. I'm going to convert that to moles of product using the mole ratio. But I have to do that for the second quantity of the second reactant. So I have to do the same calculation with my 33.8 grams of O2. I'm going to convert that to moles of O2 using the molar mass, and then to moles of magnesium oxide using the mole ratio. Whatever is the lowest number is the limiting reactant. So the smallest amount of the product determines the limiting reactant. This will be the smallest number between these two. From there, I can use the molar mass of the product. This would be my theoretical yield. It's always based on the limiting reagents. So let's add calculations here. If I consume all of my 42.5 grams of magnesium, I am going to produce 1.7483 grams of mole. Significance is to the third digit here. If I use all of my 33.8 grams of O2, I can make 2.11 moles of magnesium oxide. This is the smallest amount of product, which means this is the limiting reactant. Once I make 1.74 moles of magnesium oxide, I'm done I have enough oxygen to make more, but I don't have enough magnesium to make more. This is the excess reagent. So this is the amount I can actually make, which means this is my theoretical yield in grams of the magnesium oxide. Here's an example. If 10 grams of methane is burned in 20 grams of oxygen to produce carbon dioxide and water, what is the limiting reactant? And how many grams of water will be produced? So let's write the reaction. I have CH4 gas plus O2 gas, making CO2 gas. And water that's produced is actually a gas because it's at a high temperature. Is this balanced? No. One carbon, that's balanced. 4 hydrogens, I'm gonna put a 2 there. That gives me 4 hydrogens. But now I have 2 oxygens and 2 oxygens. I need a 2 here. This is now balanced. So I have 10.0 grams of CH4 and I have 20.0 grams of oxygen. I could pick either the amount of CO2 or the amount of water and do my stoichiometry calculations to figure out which one is produced less. I have to pick the same product for both of those calculations, but I can use either CO2 or water as that product. Notice in B, it's asking about water. So I'm gonna just determining the limiting reagent based on the amount of water produced, because that saves me some calculations at the end. So I'm gonna take 10 grams of CH4. For every 1 mole of CH4, I have 12 plus 4, I have 16 grams of CH4. For every 1 mole of CH4, I make 2 moles of H2O. So if I stop here, like we did in the example before, what I get is 10 times 2 divided by 16. That gives me 1.25 moles of H2O that can be produced from that 10 grams of methane. Let's figure out how much water can be produced if I use all 20 grams of oxygen. So for every 1 mole of O2, I have 32 grams of O2. And then for every 2 moles of O2, I make 2 moles of H2O. So when I calculate that, I have 20 divided by 32, which gives me 0.625 moles of water. Which number is smaller, 1.25 or 0.625? This is the smaller number, which means my oxygen is my limiting reagent, my methane is excess, and I can calculate the theoretical yield from this number. So 0.625 times 18.02, I can make 11.26 grams of H2O. This is my theoretical yield of H2O. This number is meaningless because I can't make that. Even though I have enough methane to make it, I don't have enough methane to actually do anything else, right? I mean, I don't have enough oxygen to react with that excess methane. I could calculate how much methane is left over. This is a calculation you're going to see in limiting reagents as well. So to do that, I'm actually going to take my 20 grams of O2 and figure out how much methane actually reacted with the 10 grams. It's going to be a lesser quantity, or how much methane actually reacted with the 20 grams of O2. It's going to be a lesser quantity than that 10 grams that I started with. So for every 1 mole of O2, actually that goes on the top, sorry. I have 32.0 grams of O2 for every 1 mole O2. Using the balanced chemical equation, for every 2 moles of O2, I need 1 mole of CH4. And if I want to calculate the grams that was actually reacted with that amount of O2, I'm going to say for every 1 mole of CH4, I have 16 grams of CH4. So the amount of methane that was consumed using all of my 20 grams of oxygen is going to be found out by this calculation. So I have 20 times 16 divided by 32, enter, divided by 2, enter, and that's going to be 5 grams of methane. This is used in the reaction. So if I want to calculate the amount of methane left over, I started with 10 grams. I used 5 grams. I have 5 grams of methane, and this is the leftover. So this is another calculation that I can get from limiting reagents. Here's another example. Lithium oxide is used aboard the space shuttle to remove water from the air supply according to this equation, and it is balanced. So this is balanced. I don't have to go ahead and balance it. I want to remove 80 grams of water, and I know that 65.0 grams of Li2O is available. So of those, which reactant is limiting? How many grams of excess reactant remain? And how many grams of lithium hydroxide can be produced? So this is what we're going to do. I'm going to find out the amount of lithium hydroxide that can be produced using the 80 grams of water and the 65 grams of Li2O. So 80.0 grams of water for every 1 mole of H2O. I have 18.02 grams of H2O. For every 1 mole of H2O, I can make 2 moles of lithium hydroxide. So that'll tell me how much lithium hydroxide can be made if I have all 80 grams to be removed. So I'm going to do 80 times 2 divided by 18.02, and this gives me, this is mole, so this gives me 8.88 moles of lithium hydroxide will be produced if all 80 grams of water are removed. Let's see how much lithium hydroxide will be produced if I use 65.0 grams of Li2O. For every 1 mole of Li2O, I have lithium is 6.941. So 6.941 times 2 plus 16, that gives me the molar mass of Li2O. So I have 29.88 grams of Li2O. And then for every 1 mole of Li2O, I can make 2 moles of LiOH. So 65 times 2 divided by 29.88. This can make 4.35 moles of LiOH. So I actually don't have enough lithium oxide to remove all 80 grams of water. This is going to be the theoretical yield of the lithium hydroxide that can be produced in moles, which means this is my limiting reactant. So my limiting reactant is Li2O. How many grams of excess reactant remains? So how many grams of water remain? I am going to go for every 4.35 moles of LiOH. I can, I'm going to use from my reagent. Remember, I can use this directly because that's a product. Once I get either the moles or grams of product, I can use that in my calculation as well. So if I know that's the limiting, I can backtrack and calculate how much water was used to produce that amount. So for every 1 mole of H2O, I use 1 mole of Li2O, and I'm going to go ahead and get grams. For every 1 mole of H2O, I have 18.02 grams of H2O. So in this reaction, I know that I consume 78.4 grams of water. So I didn't quite get to 80, right? I have excess water. My water is excess. But I got pretty close. So this is excess. This is the amount of water that was used. So how many grams of the water remains? I have 80 minus 78.4 grams. So 80 minus 78.4, I have 1.61 grams of water left over. So that's the answer to that second one. Now, I left this in moles, but I can calculate the grams of LiOH by taking 1 mole of LiOH. I'm going to take the molar mass of LiOH, which is 6.941 plus 16 plus 1.008. And that gives me 23.949 grams of LiOH. Moles cancels. So I have 4.35, which is my theoretical yield of lithium hydroxide in moles. Multiply that by the 23, the molar mass of the lithium hydroxide I just canceled. And this is 104.2 grams of lithium hydroxide. So this is the answer here. How many grams of lithium hydroxide are produced. So again, all of these calculations are related. Once I have the stoichiometric calculation, I can go ahead and use any value. In this part here, I could have started with my 65.0 grams of lithium oxide, gone to moles of lithium oxide, then to moles of water, and then to grams of water. I'd get the same answer. It really doesn't matter as long as you understand that once I calculate limiting, everything is based on that limiting reagent. This is the theoretical yield in moles, so I can use that to figure out any of the other stoichiometric calculations, just like I can use the amount of limiting reagent that I know after I do these calculations. So they're all interrelated. The last topic is going to be percent yield. So let's think about, while I make pizzas, I burn it, I drop one on the floor, something else happened. I was supposed to make 3 pizzas based on those calculations I did before, but because I lost one, I actually only made 2. The actual amount of product that is made in a chemical reaction, so this is in lab or given, is called the actual yield. I can determine the efficiency of my process by calculating the percentage of the maximum number of moles or grams of my product I can actually make. So in chemical reactions, this is called the percent yield. So some more terms. The actual yield is the amount that is actually formed in the reaction. So this is either determined in lab or must be a given in your problem. The theoretical yield is predicted by calculation. So this is what I get in my stoichiometry product, my theoretical yield. My percent yield is the actual yield divided by the theoretical yield times 100. Here is a problem. Go back to that reaction we talked about previously. Aluminum burns in bromine liquid, producing aluminum bromide, which you need to be able to produce as AlBr3. Do I have this balanced? No. I need 2 of this, I need 2 of this, and I need 3 to balance that equation. 2 aluminum, 2 aluminum, 6 bromine, 6 bromine. In one experiment, I have 6.0 grams of aluminum with excess bromine, so I don't have to worry about limiting reagent, to yield. This is my actual yield. Calculate the theoretical and the percent yields. So I'm going to figure out how much aluminum bromide should have been made using stoichiometry. So I have 6.0 grams of aluminum. For every 1 mole of aluminum, I have 26.982. That's my molar mass of aluminum. For every 2 moles of aluminum, I make 2 moles of AlBr3. Again, I'm going to write this down even though it cancels. And then using the molar mass of AlBr3, and that was again 6.9, no, aluminum is 26.982. Oops. 26.982 plus 3 times 79.904. And again, that molar mass for AlBr3 is 266.69 grams. So if I do this reaction, what I'm going to get is 6 times 266.69 divided by 26.982. And that is going to give me 59.30 grams of aluminum Br3. This is the theoretical yield. This is what should have been made. This is what actually was made. So my percent yield is the actual divided by the theoretical times 100. So I get 50.3 divided by 59.3, and I get 84.8% yield. So this is the answer to that question. There are multiple ways that you can do that particular question. Here's another example. If in the reaction below, my percent yield is 78.25, how many grams of iron are actually produced? So my percent yield is 78.25. So I know I am using 49 grams of Fe3O4. I want to calculate the theoretical yield of iron. I want to calculate what I should have gotten, because this is actual over theoretical times 100. I can figure out how much was actually made if I know the percent yield and the theoretical yield. So let's calculate the theoretical yield. For every 1 mole of Fe3O4, I have, let's see, 3 times iron, which is 3 times 55.845 plus 4 times 16, I get 231.54 grams of Fe3O4. This is balanced, so for every 1 mole of Fe3O4, I make 3 moles of iron. And then using the molar mass of iron, which is 55.845, I know that the theoretical yield of iron is going to be 49 times 3 times 55.845 divided by 231.54, and that gives me 35.4645 grams of iron. So this is my theoretical yield. So what I have is another algebraic equation. 78.25% is equal to the actual yield, which is what I am looking for, divided by the theoretical yield, which is this. So 35.45 grams of Al, or of iron, times 100. So now I'm just going to solve for actual yield. Divide by 100, I get 0.7825 is equal to the actual yield over 35.45. I'm going to multiply by 35.45. That cancels. That gives me the actual yield in grams of the iron is 27.74 grams. So this is the iron that was actually produced in this reaction. So these percent yield calculations can be tricky. You always have to remember this equation. And remember that anytime I have an algebraic relationship, I can use this in various calculations. So that's all we're going to do today for for module 6. The next time I come back to talk, we'll be starting module 7, which is solution chemistry. Everybody have a great night, and I will see you soon. Bye-bye, all.